Welcome. This is a time series analysis course. My name is Nicole Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This is a multivariate time series lecture, and this lesson I will illustrate the estimation of the VAR model using a simulation study. We'll return to the simulation study introduced in a previous lesson. In the simulation, I simulated 3 time series following a VAR model of order 1. We'd like to see how close the estimated coefficients are from the true ones provided by phi. The most common R command used to feed a VAR model is the var R command from the VARs library. The input in the VAR function is a matrix of time series where each column corresponds to one time series and each row to one time point. We also need to specify the order. Here I use p equal to 1 since we know that the data that was simulated was from a var1 model. The output of this R command is quite complex. I'm showing you here only a portion of the output. Here we see the estimation results for the first time series. The output looks very similar to that from fitting a linear regression model since the var function does just that. It applies the ordinary least squares to each individual time series. The output provided here provides the estimated coefficients, the estimates of the pi1 matrix, as in the model notation in the previous lesson. We also have the standard errors of these estimates and the p-value of the t-test of statistical significance in the last column. What can we learn from this output? From the previous slide, the coefficients from the simulated model, hence the true parameters, are 0.5, 0, and 0 as provided by the first column in the matrix phi. In contrast, the estimated coefficients in the first column of the output are 0.526, 0.007, and minus 0.0028. The estimated coefficients are close to the true ones, but the question is, are they close enough? To address this question, we could perform hypothesis testing. For example, to test whether the coefficients corresponding to the lag 1 of the series, the time series 2, and the time series 3 are not statistically significant. To do so, we can look at the p-values for the two coefficients, which are 0.82 and 0.06. Thus, at the significance level 0.05, both coefficients are not statistically significant, thus plausible is 0. The output for the other two time series is here. The one on the left is for the time series 2, and the one on the right is for time series 3. Similar to the output for time series 1, they provide information on the estimation coefficients and the p-values for the t-test for their statistical significance. For the time series 2, the true parameters are 0, 0.1, and 0, as provided in the second column of the pi matrix in the simulation. The estimated coefficients are 0.02, minus 0.01, and 0.01. The p-values of all three coefficients are large, indicating that they are not statistically significant or that they are plausible equal to 0. In this case, we thus miss to accurately estimate pi 2. For time series 3, the true parameters are 0, 0, and 0.97 as provided in the third column of the pi matrix. The estimated coefficients are 0.02, 0.008, and 0.96, where both first two coefficients are not statistically significant since their p-values are large, and thus are plausible equal to 0 as in the simulation model. The output also provides information on the covariance matrix of the residuals, which is an estimation of the variance of the error terms, sigma. We can compare this output with the covariance of the simulated model provided below. The estimated covariance accurately captures the contemporaneous dependence among the three time series as provided by the comparison of the values of the two matrices, the true covariance and the estimated covariance. Next, we'll take a closer look at the residuals of the VAR model fit. For that, We can use the residuals R command to extract the residuals which are approximate of the error terms of the three regressions. The residuals of the three regressions all stack up into one vector. We can assess the normality using the hypothesis testing procedure, where the null hypothesis is that the data, the residuals in this case, are normally distributed. For this, we can use the normality.test R command. We can also evaluate whether the residuals have constant variance by applying the arch-test R command, which is a hypothesis testing procedure where the null hypothesis is that the residuals have constant variance. For both, we seek large p-values, that is, we do not want to reject the null hypothesis. This is the R output from these two tests. The normality test provides inference on multiple aspects of normality, including skewedness and kurtosis, where the former is a measure of departure from symmetry and the latter is a measure of a departure from normal tails. The p-values for the normality test are all larger than 0.05, indicating that we do not reject the null hypothesis of normality. Similarly, for the arch test, the p-value is large, indicating that we do not reject the null of constant variance. We can also plot the residuals. Here I'm looping over I from 1 to 3 and plot the residual plot and the normality probability plot for the residuals of each of the three regressions of each of the three time series. Here are the plots. There is not a departure from constant variance or normality, as also provided by the testing procedure from the previous slide. Another assumption to be evaluated is the independence assumption. To note that we cannot evaluate independence, but we can assess whether residuals are uncorrelated. We can do so through studying the autocorrelation plots, but also using a hypothesis testing procedure for uncorrelated data called serial test in R. The null hypothesis of this test is that the residuals are uncorrelated. This is the output of this test. We discussed this test before for univariate time series. The p-value is large, indicating that the residuals are uncorrelated. Hence, it is possible to have modeled the serial correlation in the three time series appropriately. These are the autocorrelation and cross-correlation plots. The autocorrelation plots indicate that the residuals from each of the three time series look like white noise. Interestingly, the cross-correlation plots show that there may be some contemporaneous correlation among the residuals, since the bar of the zero lag is outside of the confidence band. In summary, in this lesson, I illustrated the estimation of the VAR model using a simulation study. Thank you.